Alright, I've just reinstalled and rebuilt my computer. Well, rebuilt the computer and reinstalled Windows and all that crap after the whole thing just basically died on us. So let's hope it stays alive. So anyway, I'm going to do the solutions to the various problems that Mr. Rose didn't do solutions for from problem set 1. I mean problem set 1, what am I saying? Problem set, what is it, like 13, yeah. Haha, problem set 1. Remember how easy that was? I don't even remember what it was, but I'm sure it was really easy compared to what you guys are doing now. Okay, and I've already made a mistake. So let's see, M2, there we go. So this is problem 1 from that set, where we've got M2 and M1, and they're connected by this cord here. And you got a force F pulling on M1, and they're both heading to the right over what looks to be Badlands National Park. Let's see, there we go. Alright, it's not supposed to be a slope. That's just how crappy my drawing skills are. So, let's see, we've got to find, and we've got coefficient of kinetic friction. Friction is mu sub k, and we want to find the tension. Yeah, man, I can't write it all. Tension in this thing there. Okay, actually, I'm gonna in connecting rope or string or whatever the hell it is. Who knows? Anyway, odd that I'm drawing kind of slanty. Maybe I'm holding the tablet at the wrong angle. Anyway, I'll try to fix that. So anyway, so this one was kind of difficult, you know, for understandable reasons. So it's a two body problem, which means you have to do a separate free body diagram for each body. Or there's one other choice you can do, and I'll show you that in a minute. So let's see, what else do we know? We know these things are accelerating to the right, so they're accelerating that way. Boom, like that. Okay, so there are a couple ways to approach this, but basically, when you have two bodies, you're going to have to draw two free body diagrams. I'm sorry, that's just life. So what I want to do here is, first of all, I want to show you, let's see, I want to show you just body 2. So to make this really clear, I'm going to draw, actually wait, I'm not going to do that. What I'm going to do is, let's see if I can, selection tools, excellent, alright. So I'm going to just take mass 2 and see if I can copy that and then paste it. Oh, awesome, alright. So there's my mass 2, alright. So what I want to do now is basically just sort of draw the forces acting on mass 2. So the tension in this cable, we're going to call that T. There's weight, which is going to be M2 times G. There's the normal force, counteracting weight, of course. Normal force is always perpendicular to the surface, remember. And then there is the force due to friction. So let's do a free body diagram. FPD for block 2. And this is going to be an easy one, actually, because the block is you know, all the forces are horizontal and vertical. So I'm going to set up some coordinate axes there, and we're going to make this X and this Y. So FPD for block 2. There's our little thing representing block 2, and we just put all the forces in. There's N going up, sorry, whoops, hang on. There, M2 times G, and there's tension going that way, and there's the friction force. Okay, so what we have here is sum of forces in the let's do sum of forces in the y direction first, because I happen to know that how that's going to work is equal to mass times acceleration y. Now, what is the acceleration in y? Our y-axis is vertical, right? Is it going to go up or down? No, it's going to stay there on the surface. So that's going to equal 0. And then so these forces in the y direction actually are N going up and then minus M2G. And what this tells us then is that N, the normal force, equals mass 2 times gravity. Well, that's easy, isn't it? Alright, so let's do a sum of forces in the x direction now for block 2. And that's going to equal m times acceleration in the x direction. Well, both blocks, remember, are accelerating to the right with acceleration a, so it's just going to be regular a. So this is going to equal MA. Forces in the x direction. All right, you have tension, and you have minus force due to friction, or the force of friction, sorry. Okay, now, as we recall, we were given a coefficient of kinetic friction here, right? Mu k, and friction force for a moving object, force from friction is coefficient of kinetic friction times the normal force. The more pressed against the ground the object is, the harder it is to push it along the ground. Usually that means the heavier the object is, and in this situation that's the case because the normal force is equal to the weight of the object. But that's not always true. If somebody were pressing down on the object, it could have more friction against movement, even though it doesn't, it might not weigh that much. So, without further ado, let's plug this into here. So tension minus mu k times the normal force equals ma. Well, our normal force, where do we find that? Why, let's use this green here. Normal force there we found up here. Oh my, that's awesome. All right, so and this is this is the mass of object 2. This is the M2 we're using is the mass of object 2. So it's good to keep these things straight because you can get confused if you don't take care of your variables and subscripts. So tension minus mu k times m2g equals m2a. Okay, so let's see. What we wanted to solve for the tension in this thing, right? Okay, so let's just go ahead and rearrange this for tension then. And tension equals m2 times, so I'm going to bring this stuff over here and then collect some terms. So this is going to be a plus mu k times g. Okay, so actually let me hold on. There we go. Okay, I'll write my g a little nicer. Okay, so there's an expression for tension. Now the problem is we don't know what this acceleration a is, and the problem statement did not give us permission to use a in our answer. So we have to find what a is. So I'm going to section all this off here and say, good job for now. Okay. So, but we still need to find that a. Now, there are two things you can do. One is you can do a free body diagram for object 1. And that's going to look very similar to your FBD for 2, except you're going to have tension pulling backwards on it, right? Because this cable that was pulling forwards on block 2 is pulling back on block 1. And then you're going to have this applied force F here pulling forward on block 1. So it's going to be a little different. It's going to have 5 forces, and tension's going to go the other way, and you're going to have that F in there. But it'll basically be the same. And you can solve that for A, and then you'll get some kind of expression with A and T in it, and then you can do some substitution and solve. I'm going to do something a little more radical that'll give you, and by radical I mean, radically different, not like, radical, awesome, 80s skater slang. You guys weren't alive then, never mind. So, anyway, what I'm going to do is I want to treat this entire body like one object. Wait a minute, Smith, what are you talking about? Can you do that? Well, here's what you have. You have a mass 2 and a mass 1. They're both accelerating at A, right? So it's like a whole thing accelerating to the right at the acceleration of A. What's acting on it? Well, there's an external force F, right? There's the weight of these two objects, which is going to be just, so tell you what, I'm going to go ahead and draw my free body diagram, because I'm feeling that badass right now. Okay, so, well, this isn't a free body diagram yet, but here's my like diagram of, pretending this is M1 plus M2 is how much this whole big ass thing weighs, okay? And there's a force F pulling on it, F, right? And then it's got a weight. In fact, you know what I'm going to do? I'm gonna be such a badass that I'm going to use purple, and in purple I'm going to say M. I'm going to call this just big M. Actually, no, I'm going to call it M12. Okay, M12 equals M1 plus M2. All right. So the weight of this object is M12 times G. Here's the entire normal force on this object. I'll call that M12. And then we have the friction force that's acting backwards from this object. Does this work? Is this legitimate? Okay, now let's think about what we've got here. So the weight of this object is M12 times G. Well, M12 is M1 plus M2. So really the total weight of this object is M1G plus M2G. And so that makes sense, okay, right? You've got two objects in your little system. This is like your super duper object that encompasses both of them. And the weight of this one is m2g, weight of this one's m1g. Add them up, and it comes out to be m12g. Well, okay, all right, I can buy that. Now, you have a normal force, and we're sort of saying there's a whole normal force for this whole object, which is enough to balance the gravity. I mean, we know that we're going to get there, right? So the normal force here is just the sum of the normal force for this object and the normal force for this one. So, that's going to work out too. Wait a minute, Smith, you might be onto something. Okay, and then the friction force on 1 and 2, I'm going to call it FF's 1, 2, sorry, is going to be mu times the normal force on 1 and 2. Wait a minute, is this actually going to work? Is this actually going to work? Is Smith really telling us something real here and not just smoking something? All right, hey, don't smoke, it's horrible. Okay, so FBD1. Sorry, no, hold on. I'm going to do FBD for 1 plus 2. So this is basically doing a free body diagram for the whole system. Okay, watch how crazy I am. Okay, so here's M12G going down. Coordinate axes, just to be clear on this, okay? There's N12 going up. There's the force of this rope pulling from that, not rope. Some kind of applied force here pulling on this, okay? And then to the right we have the friction force acting on 1 and 2. Okay, so sum of forces Y equals MAY, which is going to equal 0, right? So normal force 1 and 2 minus M12G equals M12. Actually, no, it doesn't equal that. It equals 0. So normal force for 1, 2 equals M12G. Okay, right? So with me so far? Okay. Now we're going to do sum of forces in the x direction on this puppy. And we're going to scroll down just a teensy tad there. Okay. Sum of forces in the x direction is going to equal ma sub x. Well, the whole thing is accelerating. Remember, the whole thing is accelerating to the right at a. So that's just going to equal ma. So sum of forces in the x direction is ma. That's F minus force of friction on 1 and 2 equals ma. This is our sum of forces in the x direction and ma. Okay, and what we have then is force of friction on 1 and 2 is mu k times the normal force on 1 and 2. So what that gets us is F minus mu k n12 equals ma. Okay, and then applied force F minus mu k n12 is m12g, right? m12g equals m12a. Okay, hang on, fasten your seatbelts because I'm about to bring this home. Alright, so we can divide by m12. So a equals F minus mu k. Geez, my writing is horrible today. Alright, F minus mu k g m12 over, that looks horrible. Alright, over m12. Okay, and then we finally just factor this out a little, and we get a equals F over m12 minus mu k g. Now, hang on, we've got a now in terms of F. Hold on, let's back up. And we just found T with an M2, an A, and this in it, right? So let's plug this A in here. So orange, this, dang it, okay. A here goes into A here. Okay, here it comes. Grand finale. I'm going to come in just under the wire on this time-wise. So T equals M2 times F over M12 minus mu k g plus mu k times g. Okay, yellow, cancel, and this goes down to tension equals F times M2 over M12. What was M12? It was M1 plus M2. So coming on down, tension equals F M2 over M12. And I would talk about this solution more, but I've got to stop right now because YouTube will only let me go 15 minutes. So there you go.